numbers. In mathematics, you must have come across expressions like this: a square plus b square plus c square plus 2ab plus 2bc plus 2ca. What will happen if we interchange, say, any two letters in this expression? Let us see. Let us interchange a and c in this expression and see what happens. A square becomes c square plus b square remains as it is, c square becomes a square plus 2 times a becomes c. So, this is cb plus 2 times b and c becomes a plus 2 times c becomes a and a becomes c. Now, observe this expression. This has a square plus b square plus c square plus 2bc plus 2ab plus 2ac. So, again you find that this expression is same as this expression. Such expressions are called symmetric expressions. So, what are symmetric expressions? An expression in 2 or more letters is said to be symmetric if it remains unaltered when any two letters in it are interchanged. A few more examples of symmetric expressions are a plus b plus c, a cube plus b cube plus 3a square b plus 3ab square. Another one can be a raised to the power 4 plus b raised to the power 4 plus c raised to the power 4 minus a square b square minus b square c square minus c square a square. They are symmetric because you can see that if we interchange any two letters in this expression, for example, if we interchange b and a, the expression remains same. Similarly, here also if we interchange any two letters a and b in this expression, this also remains same. Similar is the case with this expression. Now, look at this expression a minus b plus 1. Is this expression symmetric expression? Let us see. Let us interchange the letters a and b in this expression and see what do we get. If we interchange a and b, we get b minus a plus 1. But is this expression same as this expression? Obviously not. So, this expression is not a symmetric expression. Now, consider the terms r square p and p square r. What do you observe in these two terms? We observe that the term p square r can be obtained from the term r square p by interchanging r and p. Similarly, in the case of p square q and q square p, we find that this term q square p can be obtained from the term p square q by interchanging p and q. Similarly, this term can be obtained from q square p by interchanging p and q. Such terms are said to be of same type, that is, terms which can be obtained from one another by successively interchanging the letters involved are said to be of same type. In symmetric expressions, terms of same type occur and their coefficients are always equal. For example, in the expression a square plus b square plus c square plus 2ab plus 2bc plus 2ca, a square, b square and c square are terms of the same type and the coefficients are also equal, that is 1, and the terms 2ab, 2bc and 2ca, they are again terms of the same type. Now, look at the expression a cube plus b cube plus 3a square b plus 3ab square. What is the degree of each term in this expression? We find the degree of each term in this expression is 3. Similarly, in this expression a plus b plus c, the degree of each term in this expression is 1. Such expressions are called homogeneous expressions. An algebraic expression in 2 or more letters is said to be homogeneous if the degree of each of its term is the same. Now, consider the expression a into b minus c plus b into c minus a plus c into a minus b. Observe this expression carefully. What will happen if we replace a by b, b by c and c by a in the first term? Let us see. A becomes b, so we will get b here, b becomes c and c becomes a. This expression is nothing but the second term in the initial expression. Similarly, by the same process, b is changed to c, c is changed to a and a is changed to b. Again you find that this term, that is second term here, is nothing but the third term in the initial expression. And what happens to the third term? Let us see. C is changed to a is changed to b and b is changed to c, which is nothing but the first term in the initial expression. So, we find that each term here can be obtained from the previous term by successively replacing a by b, b by c and c by a. In other words, if the letters a, b and c are moved in a circular fashion, then the terms a into b minus c, b into c minus a and c into a minus b also move in the same circular fashion. Now, look at the expression p square into q cube minus r cube plus q square into r cube minus p cube plus r square into p cube minus q cube. Let us see again what happens if we replace in this expression p by q, q by r and r by p. The first expression becomes q square into r cube minus p cube. The second term becomes r square into p cube minus q cube, and the third term becomes p square into q cube minus r cube. Observe carefully that the first term here is nothing but the second term in the initial expression. The second term here is nothing but the third term in the initial expression, and the third term here is nothing but the first term in the initial expression. So, again we find that if the letters p, q and r are moved in this circular fashion, that is p is replaced by q, q is replaced by r and r is replaced by p, then the terms p square into q cube minus r cube, q square into r cube minus p cube and r square into p cube minus p q cube also change in the same circular fashion. Such expressions are called cyclic expressions or expressions written in cyclic order. So, what are cyclic expressions? An expression in 2 or more letters is said to be written in cyclic order if each of its term can be obtained from the preceding term by changing the first letter by second, the second by third, and so on till the last by the first. Now, look at this expression BC into B minus C plus CA into C minus A plus AB into A minus B. Is this expression written in cyclic order? Let us see. Let us replace A by B, B by C and C by A in this expression. B becomes C, C becomes A, again this becomes C minus A, which is nothing but the second term. C becomes A becomes B, and this is A minus B plus B C, B minus C. Again we find here that the first term here is the second term in the initial expression, the second term here is the third term in the initial expression, and the third term here is the first term in the initial expression. So, this expression is written in cyclic order. In mathematics, expressions in cyclic order occur very commonly. They occur very frequently in simplification of rational expressions and polynomials. Many a times we use the Greek letter sigma to represent the sum of the terms of the same type written in cyclic order in abbreviated form. For example, the expression BC into B minus C plus CA into C minus A plus AB into A minus B can be written in abbreviated form as sigma BC into B minus C in ABC. Similarly, can you tell what would be the full expression of sigma P square Q in PQR? Yes, the full expression represented by this term is P square Q plus Q square R plus R square P. Now, look at this expression A square upon A minus B into A minus C plus B square into B minus C into B minus A plus C square into C minus A into C minus B. These are three rational expressions and we have to find out their sum. For that, we need to find out the LCM of the denominator. Now, for that, just see or observe the denominators here. Here the denominator is A minus B into A minus C. In this expression, the denominator is B minus C into B minus A, and here it is C minus A into C minus B. You can very well observe that these terms are not written in cyclic order. So, let us first of all write these factors in the denominator in cyclic order. So, this expression, the first expression becomes A square upon A minus B into, if I want to change it into cyclic form, then this should be C minus A, and in that case this negative sign will come out, we will have minus C minus A. Again I will write here B square upon, this factor is B minus C, and this factor will change to A minus B. For that, this negative sign will come out, we will write here minus A minus B. Again the third expression becomes C square upon C minus A into, I want to change this C minus B into B minus C. Again for that negative sign will come out, minus B minus C. So, now this is your expression and you want to find out the LCM of its denominator. Now, your LCM becomes very easy. The denominator is A minus B into B minus C into C minus A. As you can very well see, this is a simplified form. Also, all the factors are in cyclic order. Now, the numerator becomes minus A square into B minus C minus B square into C minus A minus C square into A minus B. From all these terms, I can take out negative sign common. This negative sign becomes positive. This negative sign also becomes positive. So, now this is our numerator. Can we reduce this expression to its lowest form? Yes, if we can find common factors in both the numerator and the denominator, then cancelling out the greatest common divisor, that is GCD, from the numerator and the denominator, we can reduce this whole expression to its lowest form. But the denominator here is already in factor form. So, let us try to reduce this numerator into factors. Now, as you can very well see that this is an expression in cyclic order. There are many methods to factor such a cyclic expression. In one of the methods, first of all we will write down this expression, that is A square into B minus C plus B square into C minus A plus C square into A minus B. I have only written down the numerator because I want to factorize the numerator here. Now, first of all we will remove the brackets. A square B minus A square C plus B square C minus B square A plus C square A minus C square B. Now, we have to arrange the terms in ascending or descending order of the powers in any one of the letters. Let us say we will arrange the terms in the descending order of the powers of the letter A. So, first of all we will write down those terms having the highest power of A. Here it will be A square B minus A square C. Then next terms having A. So, this is minus, or I can say plus C square A minus B square A. Here the powers of A is A square and the powers of A is 1 here. Then plus B square C minus C square B. These two terms do not have A at all. Now, out of these two terms, I can take out A square common. I will be left with B minus C minus, if I take A common, I will be left with B square minus C square plus I can take out B C common. So, I will be left with again B minus C. This can be further written as A square into B minus C minus A, and B square minus C square can be further factorized as B minus C into B plus C plus this term as it is B C into B minus C. Now, you can see that in this term and this term, B minus C is common. So, taking out B minus C as the common factor, we are left with A square minus A into B plus C, that is minus AB minus AC plus BC. Now, B minus C is already one factor which you have got. Now, let us again arrange the rest of the terms in descending order of the power of the next letter, that is b. So, we get here b minus c into, there are two terms having power 1 in the letter b. Those two terms are bc minus ab. Then there are rest two terms do not have b at all, that is plus a square minus ac. Now, again this is equal to b minus c into, from these two terms I can take out b common, this will be c minus a, plus if I take out a common here, a minus c. But a minus c is not written in cyclic order, so we can change this to c minus a by taking out the negative sign here. So, now our expression becomes this is equal to b minus c into b times c minus a minus a times again c minus a. Now, again in these two terms I can take out c minus a common, because c minus a is a common factor. So, we have here b minus c into c minus a, and we are left with b minus a here. But again we find that b minus a is not written in cyclic order. So, we must change it to a minus b. For that we will take out this negative sign outside. So, we now have minus b minus c into c minus a into a minus b. So, these are the factors, or this is the factorization of the expression a square into b minus c plus b square into c minus a plus c square into a minus b. So, writing down this factorized form in our original expression, what do we get here? This is negative sign here first of all, and then the factors of this are minus b minus c into c minus a into a minus b upon the denominator is same, that is a minus b, b minus c into c minus a. This negative sign and this negative sign combines and we get plus sign here b minus c into c minus a into a minus b upon a minus b into b minus c into c minus a. These factors cancel out from both the numerator and the denominator, and the answer is 1. You have studied about factor theorem in 9th class. Sometimes we use factor theorem also in factorizing cyclic expressions. Look at the expression xy into x minus y plus yz into y minus z plus zx into z minus x. What will happen if we put x is equal to y in this whole expression? If we put x is equal to y, then this becomes y square into y minus y plus yz into y minus z plus zy into z minus y. Now, this term becomes 0. So, we have yz into y minus z, and in order to have this as y minus z similar as this term, we will take out negative sign outside, we will have minus zy into y minus z. Now, these are two similar terms, one is being subtracted from the other. So, the answer is 0. Thus, we see that if we put x is equal to y in this given expression, then the value of the expression becomes 0, and hence x is equal to y is a 0 of this expression or I can say that x minus y is a factor of this expression. Now, since this expression is cyclic, therefore, as x minus y is a factor, similarly we can have y minus z also as a factor of this expression and z minus x as a factor of the same expression. Now, look at this expression carefully. What is the degree of this expression? The first term is x square y, where the power of x is 2 and power of y is 1. Therefore, the degree of this term will be 3. Similarly, the degree of each of the terms here is 3, and therefore, we say that the degree of this whole expression is 3. So, in that case, how many factors can this expression have? It can have at the most 3 factors, which we have already got. They are x minus y, y minus z and z minus x. So, this expression now can be written as xy into x minus y plus yz into y minus z plus zx into z minus x is equal to or equivalent to k times x minus y into y minus z into z minus x. Since the degree of this whole 3 terms is 3 now, because we have multiplied these 3 factors, therefore, k cannot be anything from x, y, z, it should be some constant. Now, how do we find the value of this constant k? We will find it by the principle of indeterminate coefficients. In that, we compare the coefficients of like terms in the 2 polynomials if they are identically equal in degree in one variable. So, similarly, in this case also, we want to suppose say compare the coefficients of the term x square y from both the sides. Now, here it is 1, the coefficient of x square y in the left hand side is 1, and the coefficient of x square y from the right hand side. Let us see how do we get x square y. This is x, y and minus x. If we multiply these 3, we get minus k times x square y. So, that gives us the value of k as equal to minus 1, and hence the factors of this expression will be minus x minus y, because the value of k we have already found as minus 1, into y minus z into z minus x. So, today we learnt about factorization of cyclic expressions. This is very important in the field of mathematics. Thank you.